system. There is a more utilitarian view of university based on economical constraints, but we have a need to form critical thinkers. If you really need to do performance engineer to solve, have to be creative. So then what are the skills required from performance engineers? And what we concluded then was ability to work with a team, and having communication and presentation skills, to use examples, to instrument and demonstrate techniques. And then we had some ideas that Kishore probably, the special issue on education to convey workshop learnings, Coursera class on performance reliability, and create tools to share our experience, right? So how, and then the question is how to get students to take those classes, right? Which was one, which students are more interested in the programming, the Python, right? To get young students, they are really good about all the new technologies, but it's hard for when you ask them why you're doing this and what is the physics behind it, right? And what's the model, right? And why this, why you take average of those variables? Doesn't make any sense. Sometimes I interact with young students who want to take the average because the average is easy to do, but what is the meaning of it, right? Is it the proper metric for the case, right? So, then they'll have the an increasing number of women into CS and performance engineering, which is really nice. Right? And is there a fundamental problem on how performance engineering is taught today, right? So that was a question. And in some countries and some regions, you have a 50-50 gender split. In others, it's not this way, right? In specific, I was very surprised when I moved from South America to North America. In my classes in South America, it was 50-50 women and men, and here was mostly men, right, in North America, right? And how can you make performance engineer helpful to society? So how do you train students to interpret performance data, how to make it more attractive? And then there is a requirement of teaching good measurement discipline. This is something physicists, they are required to do, right? Like every physicist has to go to measurement class, or electrical engineers have to take this, right? But usually it's not taught, right? Measurement discipline is not taught in computer science, right? So how do you package performance engineering courses? How do you deal with complex systems, right? What kind of new didactics are required? How do you change the classes to fit the changing world? How to involve the students? So we can use some of these workshops for teacher training. And students are usually minimizers, right? What are the consequences of this behavior in industry? And one of the comments was that there is a need of performance engineers that can solve problems that are immediate. So usually you have a performance problem in the field, you need to have a task force, you need to address, you need to solve it immediately. How do you get this focus, right? How do you get students to have the sense of urgency? Then you need the approaches to share the materials, and you use crowdsourcing to help solve problems, right? So this was the conclusions of 2017 WEPPE. And the idea that at the end of the day, you might create a new slide with the learnings and recommendations for today. So basically you can send your ideas, your recommendations either to the Slack, we have a Slack for WEPPE, or to this Zoom chat for this one. And we should we have in the scheduled time to create our recommendations. So the schedule today is first opening, minding the gap between education and praxis. That's the presentation that I just gave, right? Then Waisita is going to present the role of analytical models in engineering and science of computer systems, followed by Maria Colarosa's team's performance and monitoring guidelines talk. Then Andrea Bondi's team is going to present experience with teaching performance measurement and testing, a course on functional testing. Then you have Christina Bad's team, an analysis of distributed systems syllabi with a focus on performance-related topics. Then Sam Kunev is going to present his experience on the new course on software on systems benchmarking for scientists and engineers. So David Daly is going to present the performance engineering and database developed in MongoDB. And Connie is going to wrap us with software performance in your education. So I expect I think all the presenters are online now. Everybody's online, correct? And then we have a discussion and summary, right? So this is the outline. So this is clear for everyone, right? So let's get started. Revise Itai. Any comments at this point? Let's make it very interactive and people can use all the methods to communicate. So I'm going to stop sharing and Wise C can present.
Should I start?
Yes, please.
Okay, so this is the 50th, this year is the 50th anniversary of Sigmetrics. And for this, I wrote a review of analytical performance modeling and its role in the engineering and science of computer systems. So what I'm going to do here is summarize what's in that manuscript. And the examples that I provide are taken from 40 papers that are described and critiqued in a book that I use to teach performance modeling. So for this summary, I'll focus on a single question of what can analytical models offer. So the first answer is that it helps you explore what is and what is not possible. So the example here is a paper about combining the resources of small cores to give you a bigger core. You combine the memory and the caches and the bandwidth and the cycles to get a bigger core. And you can reduce the size of this bigger core if you want to save energy, or you could increase the size of the core if you want to speed up the computation and meet some latency requirements. So in this particular paper, they use a very simple queuing model to help them analyze the trade-off between energy and latency and what is and what is not possible. Now, the model is very simple, and uh, people are resistant because of these simple models. The usual objection is that you make use of very simple assumptions. The distributions are memoryless. The random variables are independent, etc. That's just not realistic. But this objection is misplaced, misguided, because many models are actually robust with respect to violations of the assumptions. So to give an example, here is a paper on distributed systems, and you have multiple nodes, and the application is structured as you can replicate the components and you decide how to place the components over the distributed system. And to help you make that decision, they have an analytical model to do the calculation. And this model uses mean value analysis, MVA algorithm. And you can see that the model is actually pretty good at tracking the performance, the measured actual performance of the system. But there's something strange here, which is that the model is non-monotonic like the actual system. But the assumptions for mean value analysis actually does not offer this, would not provide this non-monotonic behavior. This means that the authors actually, in the model, the assumptions for MVA are actually violated. So despite the violation in the assumption, the model is actually able to track this behavior of the system. So no, don't worry about the assumptions. The other issue is approximations. Now you have this very complicated system, and then you're trying to capture this complicated system with just a few equations. Then of course you have to make a lot of approximations. And one very heavily used kind of approximation is what I call average value approximation. To illustrate, there's this paper that talks about how a mobile moves across multiple wireless cells. And the issue is how long does it take to download to finish your connection? And it turns out that how long it takes depends on how fast you move. The key equation in the model is something like this. And what I want to point out here is that it multiplies the number of cells visited with the average amount of time in the cell. So this is the product of two averages. Now, when in fact what they do is to take the average of the product. So this is an approximation that is very difficult to justify theoretically. But no matter, you should, it doesn't matter that you are making this approximation. You should just go ahead with the approximation and come up with the conclusions, and then validate your conclusions in the end. Sometimes the system is so complicated that it's very hard to even write equations to capture the system. And all you can do is bottleneck analysis. And a very well-known example of this is the roofline model, where they are modeling the movement of data between cache and DRAM, and looking at how fast you can do the computation. And there are two bottlenecks there. One is the memory bandwidth, and the other one is the processor speed. And by just using this bottleneck analysis, you get something like a roof line like this. And if your kernel lies on this part of the roof line, then you know that you are constrained by the memory bandwidth. And then what you do, the things that you do to optimize your computation would be prefetching, memory, processor affinity, etc. On the other hand, if you are on this side of the roof line, then you know that your computation is limited by the processor speed. And then the kind of optimizations that you could do would be how you do your parallelization of the threads. So the bottleneck analysis is enough for you to to figure out what kind of optimizations you can do. Another thing that a analytical model can help you is to simplify your parameter space. Now, in any analytical model, there is a bunch of parameters, and sometimes there are just too many parameters to worry about. So in this particular example about an analysis of Wi-Fi, the simulation shows that the data is all over the place. But what the model indicates is that if you just do a aggregation of the parameters, then all this data actually lies on a simple curve. So this is one thing that the model can do for you, which is to show you that the space is actually not as complicated as this, and the space is actually simple like this. This is talking about how the model can help you simplify the space, but the model can also help you simplify your understanding of the forces that are interacting to determine the behavior of the system. So the example here is how your microarchitecture, your reorder buffer, instruction queue, etc., are affected by soft errors. And the key equation in this particular paper is this one that shows you how the instructions per cycle is determined by the instruction latency and the critical path length. The key thing to note here is the instruction latency is determined by the hardware, but the critical path length is determined by the software. So this one equation here actually decouples the hardware from the software. Now, this is hard to think, hard to imagine it's doable, but the model shows you explicitly how to do this so that now you can analyze the hardware in isolation, analyze the software in isolation, and then figure out how they interact through this equation. So it helps you to decouple these interacting forces. when you use the analytical model to analyze a system, it is entirely, because of all the assumptions and approximations, you're not going to be numerically accurate. So if you're not numerically accurate, then it's possible that you're also analytically inaccurate, meaning that the conclusions that you draw from the model may be different from the behavior of the system, and you have to guard against that. So one example is this one that talks about how to size a router buffer to suit TCP connections. And they use a very simple MG1 model that gives them this sawtooth curve. Now, this sawtooth curve is something that I would not have expected, and I would have suspected that is an artifact of the analytical model. But the authors actually did the measurements and showed that, in fact, the real measurements themselves have this sawtooth behavior. So this is an example of what I call analytical validation, where a behavior, a property from your model is validated with the experiments. This is not a validation, not a numerical validation. It is validating the property that you deduce from the model. So what we want to do here, this is the kind of things that we want to do. We want to use the analytical model to help us extract insights, extract properties, analyze the model. So to press on further, we want to go more than that. So this one paper about CD and content delivery networks, they look at, now in the case of content delivery networks, the issue is that the objects are meant of large range of sizes. So it's not clear that you want to admit all the objects into the cache when there's a hit. So this paper looked at admission probabilities for LRU cache, and they show that the probability that an object is in cache is given by this expression. Now, that means this expression also gives you the probability of a hit. The point to note here is that this is an equation that will be valid as long as you use this admission policy, as long as you use LRU. Think about it. 50 years from now, computer technology is moving at such a fast pace that 50 years from now, many of the things that we worry about now will be irrelevant 50 years from now. But 50 years from now, there will still be caches, which means 50 years from now, this equation would still be valid. This equation would still be relevant. So we are trying to know if we want to extract a science out of computer engineering, then performance modeling is the one that will help us do it. So this is the final point I want to make, right? Yes, performance models can help you engineer computer systems. But if you want to extract some science of these computer systems, then performance model is the one that's going to help you do that. Thank you.
Thank you very much. Very nice. So you have questions now, discussions. There are some questions on the chat. Alex, you want to ask your questions?
I can, sure. So I was thinking actually about starting with a more general question, which bugs me every time I have to introduce a formula in a course of mine. So I see a lot of students scared of models and of mathematical expressions of models. Our students they're good coders, they're intelligent, but somehow they get scared of this. And yet when I see a talk such as yours, I think, how could they be scared of this? So could you care to comment? Is there a nice way to introduce them to this?
So, shameless advertisement, ask them to read my book, right? In my book, every chapter, the equations for every chapter is confined to